Good evening. This is an extra session, which is also a tutorial session for the course Basic Electrical Circuits. We'll be solving problems from op-amp, AC circuits, Thevenin equivalent, maximum power transfer theorem, as well as one problem on DC transients. Let us start the session. This is the first problem based on op-amp circuits when AC excitation is given. Find the value of I0 if the input voltage to the circuit shown below is Vi is equal to 2 sin omega t millivolts. You are asked to find the output current coming from the op-amp. Please take some time to solve this question. Hope you could solve the question on your own. Now let us discuss the solution. The equivalent circuit of an op-amp is shown, where V1 and V2 are the inputs to the non-inverting and inverting terminals. R in and R out are input resistance and output resistance. A is the open loop gain, which is usually very high. I1 is the input current, or I is the input current, and I0 is the output current. So generally, A is very high and V1 and V2 are approximately same, which is called the virtual ground, or they act as virtually shorted points. The input resistance is very high, but output resistance is low. Since the input resistance is very high, your input current is more or less negligible, but output current exists. So we don't know what your output current is, but it exists. So while solving problems on ideal op-amps, the concept of virtual short can be used. Also, we can assume that the input current is 0. So these two concepts can be used when handling ideal op-amp problems. So in the given problem, let us see how we can apply these two concepts. If you are familiar with the terms of op-amps, you know that this is a inverting op-amp because the input voltage is applied to the inverting terminal and it's a feedbacked op-amp. So this kind of a structure is called inverting op-amp. Now, the first concept is virtual short. Virtual short or virtual ground means that the voltages at both the terminals are approximately same. We know that the potential at the non-inverting terminal is ground, which is 0 volts. That means the potential at the inverting terminal is also 0 volts. So this is the first step. Now next step is that the input current is 0. That means the current entering or leaving the inverting or non-inverting terminals both are 0. So this is 0 ampere, this is also 0 ampere. So the first two steps are done. Now let us see how to solve this using basic networks equations. So now you have this current, it will reach here, but it will not enter the op-amp because its input resistance is very high. So what it will do? It will take this path. So the current which is coming from the input terminal will not enter the op-amp, rather it moves to the Sorry for the interruption. It moves to the through the feedback resistance. Now you have your output current also coming. Now there are two currents. One is the input current and one other is the output current. Now these two currents will add up and it has two paths to go. One through this path and another through this path. Now it cannot go through this path because it is open. So how that current will go? That current will go downward. So let that current be named I2 and the input current be named I1. The capital letters are denoting phasor because it is an AC circuit. Usually we represent capital letter for DC component or constant components. Here I am representing it as phasors. So for the given op-amp network, this current is I1. This current is also I1. This current is I0 and the downward current is I2. We have to find what? We have to find I0. Now I0, if you apply Kirchhoff's current law at this node, say A, at node A, the incoming currents is equal to the outgoing currents. That means the incoming currents, which are I0 and I1, is equal to the outgoing current I2. So this is the Kirchhoff's current law equation, KCL at node A. This gives you I0 as I2 minus I1. So the question is asked to find the output current. We obtained output currents in terms of two other currents, which is I2 and I1. Now I2 is the current which is flowing through the 4 kilo ohm resistor and I1 is the input current. Now we have to solve for I2 and I1 in order to find I0. As I've explained before, this potential is also 0 volt. So how can you find I1? Now I1 is a current which is flowing through the 1 kilo ohm resistor. It is also the same current flowing through 10 kilo ohm resistor. So if you draw the path of I1, I1 flows through 1 kilo ohm as well as 10 kilo ohm. The center, which is 0 volts. At this end it is VI volts and at the other end it is V0 volts. So this current is I1. This is also I1. So you can write I1 using two equations, one with the input voltage and another with the output voltage. Now with input voltage, if you write, you can use this branch. So we know that voltage is resistance or impedance times current. So that means Vi minus 0 is given by 1 kilo ohm times I1. This is I1 in terms of Vi. Now we know Vi. Vi is a phasor. I1 is also a phasor. Now what is Vi? Vi is 2 sine omega t. Now the phasor representation is according to your wish. So if I am taking my sine axis as the reference axis, then your Vi will lie on the sine axis. So this is your Vi. Now the magnitude of Vi, which is the magnitude of this phasor, is 2, because Vi of t is 2 sine omega t and this quadrant or this phasor is of the frequency omega. In this domain, your VI is lying on the sine axis, and I am taking sine axis as reference. That means I can represent VI as 2 angle 0. If that is the case, I can substitute it in this equation. So VI is 1 kilo ohm times I1. That means my I1 is VI times or by 1 kilo ohm, which is VI is 2 angle 0. That much volts or millivolts, let us see. That much millivolts. That means it is this is this much millivolts. So I can multiply it with minus 10 raised to minus 3, it will become volts, divided by 10 raised to 3 ohms. So this becomes 2 angle 0 times 10 raised to minus 6 ampere. Now 10 raised to minus 6 is micro. So the current I1 is 2 angle 0 microampere. So I can write I1 in time domain as 2. Since the angle is 0, I1 also lies in the sine axis. So V1 is here, VI is here, I1 is also in the same axis. So I1 is 2 sine omega t microampere. Now if you see this figure, you can represent I1 in terms of V0 also. So I1 is the current which flows through the 10 kilo ohm also. So this is your I1. This point is ground and this is your V0, which is output voltage. So I1 is also given by 0 minus V0 by 10K. Why I wrote 0 minus V0? Because the direction of current is from 0 volts to V0 volts. If I1 was flowing in this direction, if this was your I1, then that would have been written as V0 minus 0 by 10 kilo ohm. That is not the case here. So in here, your I1 is 0 minus V0 by 10, which is minus V0 by 10K. This is your I1. That means I can write my V0 as minus 10K times I1. Now this is minus 10 into 10 raised to 3 times I1 is 2 angle 0 into 10 raised to minus 6. That much ohm times ampere, which is volts. So your V0 is minus 20 times 10 raised to minus 3 volts. This is nothing but minus 20 millivolts. So your V0, if you represent in time domain, it is minus 20 sine omega t millivolts. That means your V0, so here is your V1, here is your I1. Your V0 can also be drawn here, but it will be the magnitude is minus 20, means what? Your real V0 lies here in the minus x axis. So your x axis is sine. X axis is sine. So your V0 is 180 degree shifted from your x axis. That is the case for inverting amplifier, inverting op amps. So for inverting op amps, your output will be 180 degree shifted from your input. Now coming back to our question, you obtained V0. So let us go back where your I2 is. So your I2 is the current which is flowing through the 4 kilo ohm resistor. So one end of I2 is at a potential V0 and other end is grounded. Now since I2 flows from V0 to 0 volts, you can represent your I2 as V0 minus 0 by 4 kilo ohm, because it is flowing from higher potential, which is V0 to 0 volts. That means you can get your I0 as I2 as V0, which is minus 20 millivolts divided by 4 kilo ohms. So this is volts by ohm. That means it is minus 5 into 10 raised to minus 6 ampere or minus 5 microampere. That means in the phasor diagram, your Vi and I1 are in phase, whereas your V0 and I2 are also in phase. So the magnitude of I2 is 5 and its angle is 180 degree. Now let us see what is your I0. You got your I0 as I2 minus I1, right? I0 is I2 minus I1. Now what is I2? We obtained I2 as minus 5 and I1 is 2. So I1 is 2. So this is minus 7. So I0 is minus 7 microampere. Now minus 7 is nothing but 7 angle 180 degree or minus 7 angle 0 degree. So it lies on the same axis as your V0 and I0. Sorry, V0 and I2. So in time domain, you can write I0 as minus 7 sine omega t microampere. So the answer is minus 7 sine omega t microampere. Now let us move to the next question. Please go through this question. Consider the circuit shown in figure with a load impedance ZL. What value of ZL will absorb average maximum power? So this is a problem on maximum power transfer theorem or MPT. So according to maximum power transfer theorem, if you have a voltage source which is having an internal impedance of ZS and you have a variable load ZL, then maximum power is transferred to ZL when ZL is equal to ZS conjugate. Now according to Thevenin theorem, you can represent a complex circuit of resistors, inductors, capacitors, so on, across any terminal AB with a simple voltage source if you are dealing with an AC circuit in series with a impedance across the terminal A and B, where this voltage source voltage is called the Thevenin's equivalent voltage and the equivalent impedance is called Thevenin's equivalent impedance. Now if this is the case, you can apply the same thing to a maximum power transfer theorem where you connect your load across this terminals AB. So across whose impedance, across which impedance you want to find the maximum power transferred, you just remove that impedance and try to obtain the Thevenin equivalent voltage as well as impedance across that terminals, and then apply maximum power transfer theorem. So you can mix your maximum power transfer theorem along with the Thevenin's theorem and solve the circuit. Now in the given problem, you are asked to find the value of ZL which will absorb maximum average power. That means you can mark this terminals as AB, and then you can find the Thevenin equivalent impedance which you obtain by looking across AB. Once you get the Thevenin equivalent impedance, then the condition for maximum power transfer to occur is when your load impedance is same as the conjugate of the Thevenin's impedance. So this maximum power transfer theorem problem got converted to a Thevenin theorem problem. Now let us see how to find the Thevenin equivalent impedance of this circuit. Now the circuit has a dependent voltage source. Now if there is no dependent voltage source, then only independent voltage sources, then how you can find the Thevenin equivalent impedance? You just have to replace the independent sources with its equivalent internal impedance. That means the voltage source you can replace with a short circuit, and the current sources can be replaced with an open circuit. And while you are looking across the terminals, you just find out what is the equivalent impedance. But in this case, since a dependent source is present, you cannot apply this method. So the other method, or the method which we use when there is presence of a dependent source, is we apply a test voltage across the terminal, and we'll see how much current is drawn by the circuit. Now the Thevenin equivalent impedance is given by the ratio of this test voltage to the test current. So let us apply this method. So we have your resistance, an inductor, a capacitor, a dependent voltage source, a dependent current source, and your terminal ZL. And there is a voltage source here, which is of 4 angle 0. This is 1 ohm, this is minus j ohm, this is j1 ohm. This voltage is Vx. This voltage is 2 times Vx. Now we have to find the Thevenin equivalent impedance. Now while finding Thevenin equivalent impedance, one method is to apply a test voltage and find how much current is drawn by the circuit. Now while applying the test voltage, you should replace your independent sources with its equivalent internal impedance. Now in this case, you have a voltage source. So the equivalent impedance of a voltage source is 0. So you have to replace the voltage source with a short circuit. And the next step is you have to apply the test voltage. So you have to remove your load impedance and you have to apply a test voltage. Now the circuit will draw a current which is test current, and your Thevenin equivalent impedance is V test by I test. So you just have to solve this circuit using any of the basic electric circuit solving methods which you studied. Now I'll go for nodal analysis. So since there are no ground mentioned in the problem, you can choose one node as the reference node or ground potential. If that is the case, this node potential is already given, which is Vx. And this node potential is V test. So now you have two nodes. You can solve the nodal equations. Now let us write the nodal equations first. Applying nodal analysis, or nodal analysis basically application of Kirchhoff's current law at node Vx. So by nodal analysis, how I will write is, I write all the outgoing currents. I express all the currents as outgoing. So you know that outgoing currents is same as incoming currents. So if all the outgoing currents, all the currents are outgoing, then the incoming current is zero. So this is how I'm going to express the nodal analysis. I'll write all the currents as outgoing currents and I'll equate it to zero. So if all the currents are outgoing, that means the potential or the node which we selected is the higher potential node. So applying nodal analysis at node Vx, I can write Vx minus 0 by 1 ohm, which is the current through 1 ohm, plus Vx minus 0 divided by J1 ohm, which is the current through J1 ohm, plus Vx minus V test divided by minus J1, which is this current. Now these are the three branches which is going out of Vx, and those currents are equal to 0. Now we can solve this equation. You can take Vx. Vx is 1 plus 1 by J1 plus 1 by minus J1 minus or plus V test by J is equal to 0. Now this becomes Vx into 1 by J1 plus 1 by minus J1, which is 0. So Vx into 1 minus J times V test, where I multiplied the numerator and denominator with J. So I multiplied numerator with J, denominator also with J. And you know that J square is minus 1. So this will give you this equation. That means your Vx is nothing but J times V test. Now let us write the nodal equation for the node V test. Now here also we'll assume that all the currents are outgoing. So this current, the first current, can be expressed as V test minus Vx divided by minus J1 plus this current which is going out from V test is minus 2Vx plus this current which is going out of V test is minus I test is equal to 0. So multiplying numerator and denominator with j gives you j v test plus Vx by j minus 2Vx is equal to I test. Now Vx you obtained as j times V test. So you can replace Vx with j times V test. So it will become j times V test plus j V test by j minus 2 times j V test is equal to I test. So j by j get cancelled out. You have j V test minus 2 j V test, which becomes V test minus j V test is equal to I test, or V test by I test is given by 1 by 1 minus j. So you can multiply numerator and denominator with its conjugate, 1 plus j, 1 plus j. So this becomes 1 plus j divided by 1 plus j into 1 minus j becomes a plus b into a minus b, which is a square minus b square. So this is 1 square minus j square. Now you know j square is minus 1. So this becomes 1 plus j by 1 minus minus 1, which is 2. So 1 plus j by 2, which is your Z Thevenin. So you obtained your Z Thevenin as 1 plus j the whole by 2. So according to maximum power transfer theorem, for maximum power to be transferred from a circuit whose Thevenin voltage is V Thevenin and Thevenin impedance is Z Thevenin, and you have a variable load which is ZL, according to MPT theorem, ZL, if it is equal to Z Thevenin conjugate, then maximum power will be transferred. So you obtained your Z Thevenin as 1 plus j the whole by 2. So the conjugate means just invert the polarity of its imaginary part. So it becomes 1 minus j by 2. So the value of load impedance which will result in maximum power transferred is 0.5 minus j 0.5 ohms. So in the given problem, you are asked to find the maximum average power transferred to the load. So you have to find the Z Thevenin. To find Z Thevenin, you have to remove the load and look across the terminals and find the equivalent impedance. But since the circuit has a dependent source, you will apply a test voltage V test and you will find how much current is drawn by it by replacing all the other independent sources with its equivalent internal impedance, and then find the ratio V test by I test, which will give you the Z Thevenin. So please go through this problem. So in the given question, you are asked to find the value of maximum average power absorbed by the load. So this is a continuation of the previous problem. In this problem, you are asked to find what is that maximum power. So these are AC circuits. So for AC circuits, power has three forms. One is a complex power. Then there is a real power, reactive power, and one more you can define, which is the apparent power. Complex power is represented by a complex number S, which is given by the voltage phasor times current phasor conjugate. So this power will have a real part and an imaginary part, where the real part is your real power, the imaginary part is your reactive power, and apparent power is a scalar quantity and it is the magnitude of your complex power. So it is magnitude of V times magnitude of I, or it is root over P square plus Q square. Now coming back to complex power, you know that the real part of your complex power is your real power, which is the average power, which is asked in the problem. Now, as explained before, if you have a circuit whose Thevenin equivalent voltage is V Thevenin and load impedance is ZL and the Thevenin impedance is ZTH, for maximum power transfer, your load impedance should be equal to the conjugate of your Thevenin impedance. Now, if your Thevenin impedance is given by RTH plus J XTH, where RTH is the resistance and XTH is the reactive component, which can be either inductive or capacitive. Then for MPT, your ZL should be ZTH conjugate, which is RTH minus JXTH. That means the sum of ZTH and ZL will be RTH plus JXTH plus RTH minus JXTH, which is nothing but 2 times RTH. Now, the current through this circuit. So I have drawn the circuit for the maximum power transfer case. That means this is equal to ZTH conjugate. Now this current ITH is given by the total voltage by the total impedance. Now VTH remains the same, VTH. ZTH plus ZL is 2 times RTH. So your ITH for maximum power transfer is VTH by 2 times RTH. Now what is VTH? Sorry, or more like your load, across the load there is a voltage of VL and the load current is IL. So you are supposed to find the power absorbed by the load. So your load is ZL, the load voltage is VL and the load current is IL. Now you know that your IL is same as ITH because it is a series circuit, which is nothing but VTH by 2 RTH. Now what is your VL? You can apply voltage division rule. So the total voltage is VTH, and according to voltage division rule, a fraction of VTH comes across VL, which is proportional to the impedance of VL across VL and by the total impedance of the series circuit. I can explain once more. If you have two impedances Z1 and Z2 across which the voltages are V1 and V2 and the total voltage across them, is V, then V1 is V times Z1 by Z1 plus Z2 and V2 is V times Z2 by Z1 plus Z2. So if you follow the voltage division rule to this part, your VL is nothing but the total voltage V Thevenin times ZL by ZL plus ZTH. Now ZL is nothing but R Thevenin minus JX Thevenin. And ZL plus ZTH is 2 times R Thevenin. So you got your VL as VTH times RTH minus JXTH, the whole divided by 2 times RTH. So this is your voltage across the load, and your current through the load IL is VTH divided by 2 times RTH. Now let us see what is the power across your load. So these conditions are under maximum power transfer condition. That means at this condition, the power transferred to the load will be the maximum power that could be transferred to the load. It is given by the real part of your complex power. Now the complex power SL, which is the complex power absorbed by the load, is given by VL IL conjugate. Both are phasors. Now VL you obtained as V Thevenin times R Thevenin minus JX Thevenin divided by 2 R Thevenin, and your IL is V Thevenin by 2 times R Thevenin conjugate. Now in this expression, only V Thevenin is a phasor, R Thevenin is a scalar quantity. So when you take the conjugate inside, it applies only to V Thevenin, because R Thevenin, since it is a real number or a scalar quantity, its conjugate is same as its own value. So now you can rewrite V Thevenin R Thevenin minus JX Thevenin times 2 times R Thevenin multiplied by V Thevenin conjugate divided by 2 R Thevenin. Now you see, you have V Thevenin and V Thevenin conjugate, that is, you have a complex number times that complex number conjugate will be magnitude of that complex number square. That means you have V Thevenin into V Thevenin conjugate. So it becomes magnitude of V Thevenin square. The rest of part remains the same, R Thevenin minus JX Thevenin divided by 4 R Thevenin square. So this is your complex number or complex power across the load. So this is a very important equation. This represents the complex power absorbed by the load at the maximum power transfer condition. Now this SL is nothing but PL plus JQL, where PL is the maximum average power across the load. Across the load is ZL, not RL, sorry. Across ZL, or maximum power absorbed by ZL. Across is used for voltage. So maximum power absorbed by ZL. Now this is PL is nothing but the real part of SL. Now you already obtained SL. So what is the real part? The real part is the part which doesn't have J. So you can rewrite SL as V Thevenin square RTH divided by 4 RTH square minus J B Thevenin square X Thevenin divided by 4 RTH square. Now the real part is this, which is your PL, which is V Thevenin square R Thevenin square will be cancelled, so it becomes 4 RTH. So this is the expression of maximum power transferred from source to load. So this remains the same for AC excitation as well as DC excitation, but in AC excitation the condition is ZL should be Z Thevenin conjugate. So you have to find PL, you have to find V Thevenin, because in the previous problem you already found your Z Thevenin. So this is your ZL. So R Thevenin is same as the load resistive component of your load, which is 0.5. So that you have this you have, but you have to find what is V Thevenin. So for the given question you have to find what is your V Thevenin. So let us find V Thevenin of this circuit. To find V Thevenin, you have to first remove the load. Now after removing the load, what is the open circuit voltage across that terminal? That is your Thevenin voltage. So all the other parts of the circuit should be remained intact because we are finding V Thevenin and not Z Thevenin. So since a ground is not given in the problem, you have the liberty to choose the ground potential, which is, I'm choosing this node as a ground potential. So this potential is 0 volts. Now I have two nodes. One node is anyway given in the problem Vx. The other node is your V Thevenin. Now if you observe, you can see that this current from 2Vx cannot go through the other path, through this path, because it is open circuited. So this whole current will flow through your minus J1 ohms. So first equation you can write through minus J1 ohms, 2Vx current is flowing. So it is flowing from the higher potential, which is V Thevenin, to the lower potential, which is Vx. So I can express V Thevenin minus Vx as minus J1 times 2Vx. So this is your first equation. From this you can get your V Thevenin as Vx minus 2jVx, or your Vx is V Thevenin divided by 1 minus 2j. So we got one relation between the two unknown voltages. Now for the second relation, we can apply nodal analysis. At node Vx. So as I have explained before, while writing the nodal analysis equation, I assume that all the currents are going out of the node, which means all the outgoing currents, all the currents are outgoing which is equal to the incoming current, but since I am assuming all currents are outgoing, you can equate it to 0. So the outgoing currents I can assume first, right, for this outgoing current. So that outgoing current is Vx minus 4 angle 0 divided by 1, which is a green colored one. Then the next outgoing current is through this J1 ohms, which can be expressed as Vx minus 0 by J1 plus the next outgoing current is through minus J, so which is Vx minus Vthevenin divided by minus J. But you know that current is same as 2Vx, which is incoming. So this whole you can replace it with minus 2Vx equal to 0. Because this branch, the current which is going through minus J1 is in this direction, in the reverse direction it is 2Vx. So while I am writing the nodal equation of Vx, I can express that current as minus 2Vx. So the other parts remain the same. So this is a nodal equation which is basically applying Kirchhoff's current law at that node. So you can take Vx outside. So Vx 1 plus 1 by J1 minus 2 minus 4 angle 0 is equal to 0. So which is written as Vx into minus 1 minus J. I can multiply both numerator and denominator of J. So minus 1 minus J is equal to 4 angle 0. So you will obtain your Vx as 4 divided by minus 1 minus J. Now you know that your Vthevenin is nothing but this relation. So the relation which connects Vx and Vthevenin is Vx is Vthevenin divided by 1 minus 2J. So from this you will get your Vthevenin as Vx times 1 minus 2J. So you just multiply 4 by minus 1 minus J with 1 minus 2J and you will obtain your Vthevenin as 6.32 angle 71.56 degree volts. So you have your Vthevenin and you have your Rthevenin. Rthevenin you obtained as 0.5 ohms. So you will get the maximum power transferred is Vthevenin magnitude square by 4 times Rthevenin, which is 6.32 square divided by 4 times 0.5. This will come out to be 19.97 watts. So this is the value of the average power, maximum average power absorbed by the load. Please go through the next question. In the given circuit, switch has been open for a long time before closing at t equal to 0. The value of current through the 5 ohm resistor at t equal to 0 plus is. So in the given circuit, you have resistors as well as capacitors. So it's an RC circuit. So this is a problem on DC transients on RC circuit. So you have three elements, which is a resistor, an inductor and a capacitor, out of which the memory elements are inductor and capacitor. That means it has the variables associated with these elements has an impact on its previous state. So when you apply a switching operation at say t equal to 0 second, then the resistor will not have much change. Resistor is whatever input is coming at that instant, the resistor's output depends upon only at that instant. But in the case of an inductor and a capacitor, the current which was in the inductor just before the switching and the current in the inductor just after the switching will be same. In the case of a capacitor, it is a voltage. So voltage across a capacitor before switching and voltage across a capacitor just after switching will be the same. So in the given problem, you are asked to find the current flowing through the resistor at t equal to 0 plus. That means you have to apply this logic in this problem. So let us redraw the circuit. Now, this is a circuit before the switching operation. That means this is a circuit at t equal to 0 minus. Now, at steady state, that means once the switching operation is done or once the switching operation is not done, either way, when the circuit reaches a steady state, the resistor will act as its own, whereas the inductor will act as a short circuit and the capacitor will act as an open circuit. So, it is given in the problem that the switch has been opened for a long time. That means before the switching operation, that is when the circuit was at this condition where the switching operation is not performed, the circuit is already in its steady state. Now at steady state, the capacitor will act as a open circuit. So you can replace the capacitor with an open circuit. So before switching means it could be any time before t equal to 0. It could be any time before the switching operation is done. But t equal to 0 minus is also a time before switching operation is done. So this circuit can also be the circuit at t equal to 0 minus. So let us write this potential across the capacitor as Vc of 0 minus. Now the capacitor is open, but it has a voltage across it which is Vc of 0 minus. Now if we find this Vc of 0 minus, we know that after the switching, this voltage remains the same, just after. So for further solving the circuit at t equal to 0 plus, we need the relations or the property of the circuit just before the switching. So let us first solve the circuit before switching. Now before switching, as I already explained, the capacitor will act as an open circuit. Now let us solve this using the normal electric circuit solving methods. So you can choose any one method. So I am going to apply mesh analysis. So first I am assuming that a current I is flowing through this. 200 milliampere is nothing but 0.2 ampere. So 0.2 ampere is flowing in this direction and I is flowing in this direction. So through this, the current is I plus 0.2. Now I am applying mesh analysis in this loop. So when you apply mesh analysis, the equation is 2 is equal to 2 volts is equal to 20I plus 5 into I plus 0.2 plus 2 into I plus 0.2 plus 3 into I plus 0.2. So this is the mesh equation, which is basically applying Kirchhoff's voltage law. So this is 2 is equal to 20I plus 5I plus 2I plus 3I, which is 30I plus 5 into 0.2 plus 2 into 0.2 plus 3 into 0.2, which comes out to be 1 plus 0.4 plus 0.6, which is also 2. So this is the mesh analysis equation. So 2 comes on both sides, that means I is equal to 0. So just before the switching in the circuit, this current I is 0. That means Vc of 0 minus is the voltage drop across your 2 ohm resistor. In this 2 ohm resistor, the current is I plus 0.2. Now this is your Vc of 0 minus. So this Vc of 0 minus is nothing but I plus 0.2 times 2. I is 0, so it is nothing but 0.2 times 2, which is 0.4 volts. So you obtained your Vc of 0 minus as 0.4 volts. Now when you draw the circuit at t equal to 0 plus, you can replace the capacitor with a voltage source whose value is 0.4 volts. So let me redraw the circuit at t equal to 0 plus seconds, that is just after switching. So I replace the capacitor with a voltage source having its initial voltage. This is 2 ohm, this is 3 ohm, this is 5 ohm, this is 20 ohm, and this is 2 volts. The question is to find this current. What is the current flowing through 5 ohm at t equal to 0 plus? Now t equal to 0 plus means the switching operation is already performed. So the switch was in this branch. So the switch is closed means it is a short circuit path. Now you have to find what is this current, that is the problem in this circuit. So it can be solved easily. You have 0.4 volt across 2 ohm. So this current is nothing but 0.2 ampere. Now you can apply mesh analysis. So you have a 5 ohm, a 2 ohm and a 3 ohm. It is closed. The current through 5 ohm is I. The current through this 2 ohm is 0.2 ampere and this is I, which is 3. So if you apply Kirchhoff's voltage law across any path, say this path, you become 5I plus 0.4 volts plus 3I is equal to 0, or your 8I is equal to minus 0.4, or your I comes out to be minus 0.05 ampere. Now this is this much into minus 0.05 into 10 raised to 3 milliampere, which is nothing but minus 50 milliampere. So this is how you solve problems at particular instant just before and after switching. For an inductor, just before switching you just find out what is the inductor current, and just after switching you replace the inductor with a current source having that much current. But for a capacitor, if the voltage across a capacitor just before switching is Vc of 0 minus, the equivalent circuit at t equal to 0 plus, you have to replace the capacitor with a voltage source with polarities retained and its value is Vc of 0 minus. Now if the question is asked for any time t, then you have to go for Laplace domain analysis, where you have to replace the inductor with Ls and a capacitor with 1 by Cs. That's all for today's class. Thank you.